The topic of this talk is going to be robustness in machine learning. I don't need to motivate this for this audience. I think we have made tons of progress in machine learning over the past 10 years, especially in these areas that try to imitate human cognition, like computer vision, NLP, speech processing, and so on. And the goal is now to deploy these new tools, neural network, in a wide variety of applications, right? Self-driving cars, healthcare, robotics, online content moderation, and so on. I think this is all great. I think machine learning will be productive in these areas. But one thing that has changed as a result of these more high-stakes applications is that there's now an increased focus often on reliability, like how well do these tools really work when you deploy them in the real world. And I think it's a broad area. You can look at this from many angles. And one perspective I want to look at in this talk today is the role of algorithms versus the role of better training data in making models more robust. Because I think, especially if we look at it from the perspective of NLP and computer vision, we've learned a lot over the past 2 years. Specifically, the training data actually seems to be a very good lever for making our models more reliable. So this is what I'm going to talk about today. And we're going to do this in 3 parts, just to get everyone on the same page. The first part is going to be an overview of the robustness landscape in computer vision. So we see what the main robustness challenges are. And then in the second part, we'll see that a recent new breed of large pre-trained models, specifically these image text models like OpenAI's CLIP model, they've made a lot of progress on all of these robustness challenges. And then in the third part of the talk, we'll answer the question why CLIP and related models made so much progress on these distribution shifts. And the answer is going to be training data. Okay, and obviously throughout the talk, feel free to interrupt me anytime. And also the talk is going to be a little bit different from the previous 2 talks. This is all very empirical and experiment-based. So there's actually, I don't think, any equation in this talk. Cool, so let's get started. Robustness landscape in computer vision. And I think a good starting point there is always Imagenet. Obviously, everyone knows Imagenet by now. We've made lots of progress over the past 10 years. On Imagenet, by some measure now, the current models have surpassed human-level performance. Take this with a grain of salt, but I think no one would sort of like argue with the fact that the models have gotten a lot better by using convolutional networks and nowadays also vision transformers. Good, but as we said, this human-level performance, always take this with a grain of salt, because as you start poking at these models, you see that they don't really work as reliably yet as we would like. And one way that the machine learning community has made this very concrete over the past few years is by introducing new test sets to evaluate Imagenet models on. I think people have probably seen some of them. Here's sort of like 4 examples that I think give a good overall perspective on how well the models work once you go out of distribution. Imagenet v2, ObjectNet, Imagenet Sketch, and Imagenet R. For the purpose of today's talk, we're not going to go into all of the details of these data sets, how they were built, what exactly they measure, because at a high level, although they test different things, from a robustness perspective, the models behave kind of similar. So just maybe to give you a very high level, Imagenet v2, this was a reproduction that we did in order to build a new test set for Imagenet. We tried to follow the existing data set creation process as closely as possible, but it turned out that even very small variation in how you build this data set lead to noticeable performance drops. Then ObjectNet, this is from Josh Tenenbaum's group at MIT, they set out to explicitly challenge Imagenet models by telling crowd workers to take pictures of objects in unusual rotations, for instance, or in unusual locations. Like normally chairs would maybe be more in the kitchen or living room in Imagenet, but they told the crowd workers, hey, take a picture of a chair in your bathroom and the chair should be upside down. So it's clearly still a chair from a human, but probably models haven't seen this kind of combination of background and orientation in a training set. Imagenet Sketch, well, as the name suggests, this is basically all of Imagenet test set, but now only sketches, not real images, just sketches. And then Imagenet R is a bit like a supercharged version of Imagenet Sketch. The idea is not only sketches, but all sorts of renditions. This is where the R comes from, like also oil paintings, anything but the real object. Okay, good. And now the big question of all of these test sets is always like, how robust are current methods? What gives us the largest robustness gains on these test sets? And so before we look at results, we quickly need to talk about how we are going to measure robustness. And because the problem with comparing lots of models on Imagenet from the robustness perspective sometimes is that just standard in-distribution accuracy can often be a confounder. Like people have done so much work on Imagenet, these models differ often in how well they do just in distribution. So in order to understand their robustness, we need to not just look at the absolute accuracy numbers, but at differences. A little more specifically, let's say we have a model A, in distribution 80% accuracy, out of distribution 75%, and then model B is clearly better. It gets 90% in distribution and 77% out of distribution. So if you just want to deploy the best possible model here, you clearly pick model B is better in both in and out of distribution. But if you look at this from a robustness perspective, one quantity that's often, at least from my perspective, more interesting is like how consistent is the model across distribution shifts. And here, the first model, this hypothetical model A, only has a 5 percentage point drop. The second model B has a 13 percentage point drop. And now the idea is something about model A is special, makes it more reliable under distribution shift. If we know what it is, probably we can combine that insight with our model B to get a model that's both high accuracy and more robust. Okay, so this is sort of the idea here. Let's look at how this plays out on real data with real ImageNet models. So this is going to be the main type of plot we're going to look at in the talk today. So I'll go through it step by step. So we have x-axis here. This is ImageNet, standard in distribution accuracy. Y-axis is a distribution shift. Here we'll use ImageNet v2. Later we'll put the other distribution shifts on the y-axis. And then every blue point here on this plot is one ImageNet model that people have introduced over the past 10 years just to do well on ImageNet. This is a really good baseline. We'll call these standard models. And in this paper here, we evaluated as many models as we could find. So everything from the seminal AlexNet paper over widely used architectures like EGG, ResNet, DenseNet, and so on. And in the top right, we have EfficientNet, which at the time was the state of the art. Good. And I also just realized I lied. There's actually one equation this talk right is x. So this is the reference point that we want to reach, the dashed line here that tells us the model is fully robust under this distribution shift, gets the same performance in distribution and out of distribution. Good. Okay, so when you look at this plot, one thing you see is that all of these standard ImageNet models fall on a very nice linear trend. Why is a good question. For now, we'll just take this as a given because it really does happen very reliably. And what this allows us to do is basically for any ImageNet model, we can just look at this linear trend. In distribution accuracy will tell us what we should expect as out of distribution accuracy just by virtue of the model having a certain in distribution accuracy. Okay? And then our goal is we would like to move this red line up in order to make the models more robust. So we call this effective robustness in this talk. This green star here is this hypothetical robust model we would like to build somehow because it's above the red line, so our baseline. And this is a reasonable target because specifically here for this ImageNet v2 distribution shift, we actually did this experiment with a set of expert human labelers. So at the top right here, this is where humans land on this plot, right? So humans are not affected by this distribution shift from ImageNet to ImageNet v2. We would like that our models are as reliable as humans, and so we need to move this red line up. Okay, good. So the question here is, in this framework, how well do current robustness interventions do? Because people have obviously worked a lot on robustness over the past few years, adversarial training, various forms of data augmentation, various filtering layers, DRO, and so on. So the next step we did in the study here was that we just ran everything, again, that we could find, where people had released an ImageNet model for their method, and we ran all of that on this testbed, in this testbed, and put this on the plot here. And when you look at this plot now, the first thing you notice is probably this kind of looks like the previous plot. Nothing has really changed that much. And this is, I think, at a high level, indeed the right takeaway. There are a couple of data points I want to highlight. So basically now, before we had only the blue points, standard training. Now we also have the brown points. These are all sorts of robustness dimensions that people have proposed. And all the brown points on the same linear trend as the blue points. So basically, they help with the thing they were designed for, like for instance, adversarial examples, but they don't help with ImageNet v2. And the only models that help a little bit are the green points here. So I'll highlight them. These are models trained on more data. So specifically on the top right, this is a model trained by Google on 300 million images. Then the other cluster of points are models trained by Facebook on 1 billion images. And then there's one that was trained on the full ImageNet 21K classes, so about 20 million images. So that helps you a little bit, but at least it's the only thing that helps consistently. Okay, good. So maybe something is fishy about Imagenet v2. So let's look at the other distribution shifts I mentioned, not just the ones that I built. So ObjectNet is the one from the MIT group, and at a high level, the plot looks kind of similar, right? So you have the blue points. It's a little bit more messy now, but you still have a pretty good linear trend that the blue points follow, and the only points that stand out here in the higher accuracy regime are the green points, the same models we've seen before, trained on more data. And again, the brown points here, they're maybe a little bit above the trend now, but overall only in a pretty low accuracy regime. Okay, and then we have two more. This is ImageNet Sketch and ImageNet R. And again, by far the best models is this cluster here of more data models. Here, data augmentation does help noticeably. So for some of these shifts, special data augmentation techniques can give you robustness, not as much as the more data models. And for some reason here, there's a cluster of adversarially trained models. I've highlighted them here in yellow. I don't know what they do. But one thing to keep in mind is it's not something you should be doing, because this model here is the result of applying adversarial training to a model that's just over here on the blue line. So when you apply adversarial training, you're just moving to the left. You're making the model worse on the x-axis, but you're not helping on the y-axis. I think Ross has a question.
The green points, do they correspond to models that were on that original line just with more data?
That were on the original? Yes, exactly. These are the same architectures. Yeah, good question. So let's make sure we're on the same page here. So these blue model points here, they all involve the same training algorithms and architectures, hyperparameter settings that you also have with the green points that are more robust here. So the only thing that changes is the training skill.
My question was, like, generally, are those green points moving kind of up or kind of towards that dot dash line?
Both. For these, it's both, but I mean, they also move. I mean, they do move up, because if you only make the architecture better, then you always stay on the red. Like if you only train on Imagenet and you only improve the architecture, then you stay on the red line. Yes, question?
So on the next slide, where some of them actually are below, is that because they improved on, maybe their performance was worse before, but they got better once they trained on more data, or?
Yeah, it's a great question what's going on with these models here. So one thing of piece of information for background is all of these green points, which are below the line, they come from the same group at Google. I don't know what they did, but this is sometimes the tricky thing. It's great that they released the models, but we don't have full access to all of the training details. So I don't know what they did, but it seems to actually hurt. Yes?
So more data, is it like a single data set with more data points, or is it multiple data sets?
This is a good question, because these more data models, again, it's not like super transparent. I mean, it's technically speaking one data set. It's a Google internal data set. This is JFT 300 million. So 300 million images that they use at Google many times to train image models. So image models, image classification models. These guys here, this is 1 billion images from Instagram. Cool, yeah, we'll see this soon, that the training data does play a key role here in how you assemble it. Cool, any more questions? No, okay, good. So this was sort of like state of the art until early 2021. And then early 2021, the OpenAI clip model came out. So basically at the time, I was a little bit pessimistic about things, because yes, it is true that more data helps here, but on some of the distribution shifts, the effect is very small, right? So like the drop here is 10 to 12 percentage points. You do get 1 to 2 percentage points above the line from 1,000 times more data, right? So like Imagenet is 1 million data points. The Instagram 1 billion data set is 1,000 times more data points. So if you naively extrapolate it, you need sort of like 10 to the 10 times more data to fully close the gap. I mean, it's obviously silly, right? It's not going to happen. But it turned out that the more data models actually had a lot more robustness left. We just didn't realize it at the time. And the paper that made us realize this was this very nice paper from OpenAI on CLIP, connecting text and images. So what they did in this paper is pre-train a large model on paired image and text data. I explained it in a little bit more detail in a couple slides. And so why this was exciting for many reasons. One of them, robustness, because the numbers that they got on these out-of-distribution test sets were just really, really good. So this is out of their blog post when they announced their CLIP model. The first result they had in the blog post were their robustness numbers. And what they do in this comparison is exactly this effective robustness comparison, right? So CLIP VITL, their largest model, they compare it to an Imagenet trained ResNet 101, and they do the comparison so that you have the same Imagenet accuracy. So basically, this is like effective robustness. You compare the same X value in the scatter plots, and then we can see what's happening on these out-of-distribution test sets, and the gains are just very, very large. Plus 6 percentage points on Imagenet v2, then plus 51 on Imagenet R, plus 40 on ObjectNet, plus 35 on Imagenet Sketch. So when you work with Imagenet, just for context, like people often publish papers nowadays when they get sort of like 1 percentage point accuracy improvement, right? These are very competitive data sets that people have worked on for many years by now. So these are very, very large gains. Like you very rarely see even double-digit gains, and OpenAI just came out and these like large double-digit improvements. So I found this super exciting, and then wanted to understand in more detail what's going on there. Cool. So just for background, let's talk a little bit about what CLIP does, because an interesting aspect about the CLIP model itself is that nothing there from the architecture perspective was really designed with robustness in mind. They have an extremely robust model, but if you look at the architecture, you wouldn't know where it's coming from. Okay, so how do you train CLIP? Basically, kind of 3 ingredients. You have an image encoder, like think a ResNet or a vision transformer that just takes images and produces a, say, 1,000-dimensional vector. And then you have a text encoder, which takes the associated text, feeds it through transformer layers, and then also gives you a 1,000-dimensional embedding. And then what you do is, as a loss function, you use a contrastive loss. So you're saying, we want that the embeddings for text and images coming from the same example, so the paired image and text data, those inner products should be large, and all of the other inner products, so images and text that don't correspond to each other, those inner products should be small. Okay? And then you train this on 400 million images they collected from the internet, and you train this with sort of like on a couple hundred GPUs for a couple weeks. So the model scale is about 300 million parameters for their largest models. Okay, so now we have our trained text encoder and image encoder. And what we are going to do with it next is, well, okay, we actually want to use this for classification. And this is also a very nice aspect of the paper. They introduced what they call zero-shot inference. So right, normally when you have a pre-trained representation from Imagenet or another large data set, you still need to fine-tune that to actually get an Imagenet classifier out. Because the only way that a representation knows about the Imagenet classes is from fine-tuning. The nice thing with this image text setup is you can use these models in a zero-shot way without any fine-tuning. So what you do is the following. You just tell the model the names of your classes. So for instance here, plane, car, dog, and bird. You make captions out of it, sort of like fake captions, like a photo of a plane. You feed this through your text encoder. So you do this once for each of your classes. We have k classes. Now we have k text embeddings. And then at inference time, you compute the image embedding for your input image, and then you just do nearest neighbor in your text embedding space. And that way you can use this out of the box as an image classifier without explicitly fine-tuning on any more image data. Okay, cool. Any questions about how this CLIP stuff works? Yes?
So during the training of the model, there's really no real text data that goes with the images. You kind of generate them?
No. There is true text data associated with the images. So like they didn't just harvest images of the internet. They went to places where you get image and text data together. Let's say Reddit posts, you have the image and the stuff they write next to the image. Wikipedia, you have the image and you have the caption for the image. So, sources like that. So this is key. This is why that works, that you have this semantically paired image text data. If you look at the training data, it's surprisingly noisy, but it works.
But in the previous models that you were showing up to this point, they're not using any text.
Yes, exactly. This is an important distinction. All of the other models we've looked at so far, they were just sort of like the standard 1 out of k multi-class classification, no text data. And this was like a big hypothesis or question here, did the text data cause robustness? And we'll get to that in a minute. Any more questions? No. Okay, good. So let's look at how the CLIP models behave when we put them into our scatter plots. So this is again out of the CLIP paper. x-axis Imagenet, they just pragmatically on the y-axis averaged over 7 natural distribution shifts. Overall picture doesn't really change. The blue line is the baseline Imagenet trained models. The green points were the prior more data models. And then the orange line is CLIP and zero shot. So like, if you look at this, it's obviously much better, right? Like we would like to be at y equals x, and so like it closes roughly half of the gap to y equals x. And there are many interesting questions coming out of this. One is, okay, why is this so robust? Another one is like, what happens with fine-tuning? Ignore the purple line, we'll not talk about this one. The red line is what you get if you take the orange points, so orange point zero shot, if you fine-tune on Imagenet, you get the red line. So you do get better on the x-axis, but you fine-tune on Imagenet, makes sense, we get better on the x-axis, but we're actually only moving horizontally. And if you look more closely, especially depending on the distribution shift, we're actually moving down a little bit. So fine-tuning on Imagenet removes some of the robustness that these models have. So another important question here was, can we get the best of both worlds? Like fine-tune these models in a way so that we have good in-distribution performance on a target task and good robustness. Okay, so this is what we did together with many great collaborators. So Mitchell and Gabriel led this. Basically, we were asking, okay, can we fine-tune these CLIP models in a more robust way? And the answer is yes. And sort of like mechanically what you do is very, very simple. So let's look at this in a schematic plot. X-axis in distribution, y-axis out of distribution. Fine-tuning moves right, but unfortunately down. How can we move basically just right in these plots when we fine-tune? And the answer is as follows. You take your zero-shot model, you just take the weights, you fine-tune the model, as you normally would, and then you just linearly interpolate between the weights. When Mitchell told me about this the first time, I thought this is pretty crazy because the whole point of these neural networks are that they are nonlinear. There are all of these nonlinear activations in them. But Mitchell and Gabriel are very creative experimentalists, so they were like, I don't care, I just linearly interpolate the models. And this actually works surprisingly well. So basically, this is the trade-off curve that you get by varying alpha between the zero shot and the fine-tuned model. And then now the question is, how do you choose alpha? Pragmatically, alpha 0.5 works very well across all the data sets we looked at. And then basically you get the performance benefits of fine-tuning while maintaining robustness at the same level of your zero-shot model.
Sorry, what is a zero-shot model?
Oh, so zero-shot model is what we, sorry, let me just repeat this to be clear about this again. A zero-shot model is this type of model that you can evaluate without fine-tuning. So basically you can take the CLIP model. It has never explicitly seen Imagenet before. It's not fine-tuned on Imagenet. But because the CLIP model is flexible in the sense that you can make it a classifier for any classes just based on the text data, you can apply it to Imagenet without fine-tuning on Imagenet. So this is why we call it zero-shot. There's no explicit adaptation step. So sometimes when people talk about fine-tuning, they talk about few-shot fine-tuning, like fine-tuning with like 10 examples per class. And so there's like this k-shot fine-tuning. If you let k go to 0, then you basically get the zero-shot inference. Cool, thanks for clarifying. Yes?
Yeah, I was just wondering, so if I understand the claim here, if I would take this 400 million image data set and then harvest from that examples that are exactly the Imagenet classes, and then train saying this is a dog, this is a car, I would still be on that line and I wouldn't see this robustness.
Oh, this is great. So we do exactly these experiments in like 10 minutes. So we'll answer it in 10 minutes. Good. Thanks for the awesome question. Yes?
For this interpolation that you had, I think, on the next slide, has anyone looked at what that means in terms of the geometry of the loss landscape, the fact that you can, that this works? I agree, it's sort of surprising.
Yes. No, actually, like the sort of like experiments people did in the loss landscape perspective were the motivation for doing this. So people had observed that if you take two models, say Imagenet models, you don't pre-train, you just start from random inits, and then you you train them, and then you look at the linear path between them, then you don't get good models in the middle. So this is, people study this under like linear mode connectivity is the term. Or like in general, when are the endpoints of training on these data sets connected? And often you can find nonlinear paths between the solutions. Sometimes you can find linear paths, especially if you use the same pre-training. Yeah, it's a good point. There's a lot of nice experiments in this direction. Yes?
Does it typically follow that shape of trajectory, or can it also like do that, or is it?
We have ever only seen it do this like nice, almost rectangular thing. Cool. Okay, any more questions? Yes?
What does the curve look like if you did early stopping?
Good question. So we have all of these ablation studies in the paper. I don't have them in this talk. You can get similar-ish curves with things like early stopping or regularization, like L2 regularization to the zero-shot model. The curve you get from this weight space interpolation is usually better. Sometimes it's just a little bit better, but it's usually better. Another nice thing of doing it that way is that you don't need to tune these parameters and fine-tune multiple times. You really just need to fine-tune once, and then you can, after the fact, do the interpolation. Cool. Okay, this is more like a side story here. I think this is more, for me, was an example. I just want to understand how widely can you use these clip models, because one concern sometimes is that, well, maybe we are just getting better on Imagenet, and Imagenet in the end is a toy data set. Like, are we actually making progress more broadly with our vision models here? And I think this clip model was a very nice example that the answer is yes, because once you have this clip model and you figure out how to fine-tune it, you could get improvements on all sorts of data sets. One nice example is the Wiles data set. I think this is a very nice data set because this is actual application data, real-world distribution shifts. So this is always a good sanity check to see whether the models do better on real data as well. And then the answer is yes. So this is iWildCam, so camera trap wildlife photos data set. And then you can compare with like these VIT models with our specific optimized fine-tuning, but without already they are substantially better than prior models only trained on Imagenet. The same is also true for another data set from Wiles, FMOW. This is now satellite data. If you look at only Imagenet here, sort of like the larger architectures on Imagenet had like 62% on the in-distribution set, and you get up to 76 for clip, and also out of distribution. It's a large improvement. Cool. Okay, so like overall high-level point is these models are really good. Why are they so good? I think we already hinted at that. There's a question like what role does the language play, and where does all of this robustness come from? Cool, and this is like the third part of the talk now, and this is going to be about this paper that we put on arXiv a couple months ago, is specifically looking at the question, where does CLIP's robustness come from? Because if you look at CLIP and so standard supervised Imagenet training, there are many ways these models differ. So the obvious one is language supervision. CLIP has language supervision, but Imagenet training does not. Another hypothesis is the training distribution. For Imagenet, well, okay, we have the Imagenet training set. For CLIP, we actually don't know exactly what they trained on. Their training set is private to OpenAI. So they are not going to release it. We asked them multiple times. They're very apologetic about this. They told us many things at a high level about their data set, but they're not going to release it. One obvious difference is the training set size. So CLIP was trained on 400 million images. Imagenet is 1.2 million images. We changed the loss function. When we do CLIP training, we have a contrastive loss function. So Imagenet standard supervised learning is the more common supervised, often cross-entropy losses. Another difference is test time prompting. Once you have this ability to do zero-shot inference, people started trying all sorts of things on the text input side to tune the models that way. Maybe that helps with robustness. Imagenet models, standard trained, can't do that. And then the last hypothesis we looked at is model architecture. I already mentioned that like the latest generation of image classification models now use these vision transformers. Also, the CLIP models use vision transformers for their best models. Imagenet models are often convolutional neural networks in the plots that we saw. Good. Okay. So this is a lot of hypotheses to go through. Fortunately, we already knew from prior work that we can rule out two of them. So one of them that we can rule out is model architecture. So OpenAI already studied that for us, which is nice. So, right, we looked at this orange line here, which is the zero-shot models, the zero-shot CLIP models. And one nice experiment that OpenAI already did was they did this CLIP-style training both with CNNs as image encoder and with vision transformers as image encoder. And when you do this with various VIT sizes and various ConvNet sizes, you're exactly on the same orange trend. So basically, architecture doesn't play a role here. And this is also what we observed already before in the just ImageNet world. So you look at all of these different architectures, people propose an ImageNet, they're all on the same blue line. And also vision transformers. If you just train them on ImageNet, they'll also fall on the blue line. Okay, good. So model architecture is out. Next thing is training set size. And this is a pretty natural one because while 400 million images is a lot more, fortunately, when we look at robustness in terms of these linear trends under model variation and everything, you can also rule out sheer model size. So what do I mean by this? So one experiment we did before, all of this came out already, was the following. So, okay, we observed in this ImageNet world that the more data models, like 1 billion images, they gave you some effective robustness. They moved you above the red line. So a natural hypothesis was that fewer data will hopefully move you below the red line to see that data plays a role here. But then it turned out if you just take ImageNet and you subsample that IID, you're moving exactly along this red line. So you take ImageNet, subsampled by a factor 2, 4, 8, 16, 32, train a model on subsampled ImageNet, moves exactly along this trend. So this is not responsible for robustness. Okay, so this is also out. Good. So now the remaining 4 hypotheses here we'll now rule out one by one in this paper. As background, we need to tell you, or I need to tell you about one more data set. And this is because CLIP, we just don't know the training distribution. What can we use instead? And what we'll use instead is a data set called YFCC 15 million. Okay, so YFCC is the Yahoo Flickr Creative Commons data set. This already came out into 2000s. This is a large image text data set, about 100 million images. And OpenAI released a subset of YFCC that, according to them, is representative of their training data. So they were like, sorry guys, we can't give you our actual training set, but here's 15 million images from YFCC. That's basically the same as our training set, just smaller. And actually, this YFCC subset is also part of their training set. Okay, and here are a couple examples where it's images with text. And the cool thing is we tested this, and this is indeed, from this robustness perspective, very reliably the same distribution. So again, scatter plot, x-axis ImageNet, y-axis ImageNet v2. And now we extended this into a much lower accuracy regime, down to 5 percentage points on the x-axis. And these light blue points here are just ConvNets again, trained on ImageNet. So they're early stopping or smaller subset of ImageNet. So they're lower accuracy regime. And then we also reproduce CLIP training. And we trained CLIP models only on YFCC. And then the cool thing you see is that in the top right, the purple stars are the OpenAI trained CLIP models. And if you extend this purple trend all the way down to the low accuracy models, these YFCC trained CLIP models with 1, 3, 7, or 15 million data points are exactly on the same linear trend. So this is indeed, I think, a valid claim that YFCC is a good approximation of their training set. Okay. Good. And with all of these things in place now, let's talk about the 2 main experiments we ran in order to figure out where the CLIP robustness comes from. Like at a high level, the main contenders were training distribution and language supervision. And basically, what we had already in the literature was supervised learning without language on ImageNet. This is basically what everyone did for 10 years. And then we also had contrastive, so with language on YFCC. And obviously, for a controlled experiment, you would like sort of like the full grid here, so you can compare by holding one factor constant. So this is what we did. Basically, we did CLIP training on a text-augmented variant of ImageNet, and we did supervised image-only training on YFCC. So this is what we'll talk about next, these 2 experiments. Any questions before that? Mm-hmm.
How were the captions used for the upper?
Great question. Let's talk about that. Imagenet captions. So the ideal comparison would be ImageNet with and without text annotation. The problem is ImageNet as a data set does not have text annotation. So what do we do? So there were a couple of possible options that we were thinking about. One was, okay, we could just make fake captions with templates, right? Like all of German Shepherd images could get the text or photo of a German Shepherd. It's a little lame because it's quite different from the language you get on the internet, and we would like to have something as close as possible to real Flickr text, because YFCC was text and images from Flickr. Another thing to get more variety into these captions would have been running image captioning models, right? This is a task people study in vision and language. Here's an image, write a caption. The problem is then you're bringing in all these biases from the image captioning model. So this is also not super controlled. More work, but possible would have been, let's just go back to mTurk and show the images to mTurk workers and ask them to write a description. Possible, but a lot of work. mTurk is expensive. So what we realized after a while is that we may be able to extract the original text annotations from Flickr, because a large chunk of the Imagenet training set came from Flickr. The images on Flickr always have text. We just didn't know how to link the Imagenet training set with the Flickr images. So, and then we did a lot of data wrangling, went back to the Imagenet metadata. Vaishal is really great of that, and Vaishal managed to connect about 500,000 Imagenet images back to their source IDs in Flickr. So for those 500,000 Imagenet images, roughly half of the data set, we then were able to just get the original caption data off of Flickr. Okay, in this data set we call Imagenet captions because it's as close to YFCC as possible from the perspective of like, let's just take images from Flickr with the text that humans uploaded with the image on Flickr. Okay, and this is how these examples then look. Like image of a duck, title reflected duck, no description. So there are 3 types of text that humans can assign to these images on Flickr. Like a title, and typically a longer description, and you can also assign tags. And like the next one is silent rocker. Description, Moses' mother has left the building, and then we omitted more because there was only so much space in the paper. You get the idea. It's like real text of the internet. Okay, and then we had that in place, and then we could train models. Okay, so let's do that. X-axis Imagenet, Y-axis average over various distribution shifts. Blue line is baseline, Imagenet trained models. Purple line is the CLIP zero-shot models, they're more robust. If you do YFCC training with CLIP, then you land at the pink squares. But then if you take CLIP and you train on Imagenet captions, then you end up exactly on the blue line. Right? So this tells us that adding the text data to Imagenet has no impact on robustness. Right? Robustness is being above the line. If you do Imagenet captions plus CLIP training, you end up exactly on the blue line. I think, Ross, you had a question?
So for the images you were able to match back to Flickr, did you notice any like bias in the ones that you were able to do? Like it was more recent ones because they were still on some server or something like that?
That's a good question. All of them are pretty old, right? Because they're all 2010 roughly. What we did was we trained supervised models only on that subset, and they're on the same blue line as well. So from the perspective of the scatter plot robustness trends here, there was no bias. But yeah, that was a good point. Any more questions? Yes?
Yes, along a similar line with that, did you see anything quantitatively? I mean, just looking at the ones that you put on here, the text don't seem very descriptive for this ones that you put on Flickr versus the ones that are coming from the clip data set. Did you guys see that quantitatively, that there was a big difference in the quality of the text?
Oh, no, this is a great question. It depends on how you measure text quality. I think we looked at basic things like just like what languages do we have in there. Yeah, I think would be a great question. Yeah, if you have ideas, happy to run it. And we didn't look into that too much because for us this was like all English text. From eyeballing it, it kind of looked like YFCC. Okay, good. So this was one way. So we took a image data set, we added text, no gain in robustness. Now we also wanted to go the other way. Can we take an image text data set where we have robustness, throw out the text to the extent possible, can we still maintain robustness? And this is what we did with YFCC classification with minimal language supervision. Okay, so as we already said, YFCC 15 million. If you train a CLIP model on that, you get a robust model. How can we get rid of the language supervision? And so like what we introduced to do that is what we call as a baseline no clip. So the first step is take the images, throw away the text. Then we have, and then you just run SimClear on it, right? SimClear is a standard self-supervised representation learning thing. Now we have a representation trained on 15 million images. It's good. The only problem is you can't use this as a classifier, right? Like the representation has like no idea what text is. It's really just mapping images to a 1,000-dimensional vector space. And okay, one thing now you could have done is like just fine-tune, but we know that fine-tuning messes up robustness, so we didn't want to fine-tune. So, we didn't want to fine-tune on Imagenet, because when you fine-tune on Imagenet, as we've seen earlier, that messes up the robustness. So we wanted to fine-tune on something that's only YFCC, and we did this as follows. We took the text now of YFCC, and we just did a substring match to the Imagenet classes. Like if there was a text and it contained German Shepherd, then we said, okay, this image belongs to the class German Shepherd. And this way we could build a subset of YFCC that we call YFCC hard match. And that is what we used for fine-tuning. So this is the only text processing in this pipeline. So no sort of like big transformer models anywhere. And the only way we touch the text is via substring matches to build YFCC hard match. And then when you fine-tune these models on YFCC hard match, then you in the end get out a model that you can use as an Imagenet classifier. Yes?
What did you do when there were like multiple substring matches or no substring matches?
That's a great idea. I don't know if Alex is in the audience. He would know, Alex or Vaishal. We probably put them into both classes. Okay, good. So this is what we did. Let's see how it looks on the scatter plots. And so this is where they end up. So now we have the orange diamonds. This is the snow clip baseline, YFCC SimClear plus classification. And it's basically pretty close to where the clip models are, right? So with the green points, that was clip on Imagenet captions. Now we have no clip on YFCC, and we get almost the same robustness. It's maybe a little bit lower, a bit hard to tell, but it seems like you could get at least a large chunk out of the robustness from YFCC with minimal text supervision. Good, okay, so let's go back to our hypotheses. So we can rule out language supervision. The last two that were left were loss function and test time prompting. And those are less interesting, so we'll just quickly go over them because we're also kind of running out of time. Okay, so effect of test time prompts. We just tried a lot of different prompting strategies. They had no impact, no interesting impact on the effect of robustness. So basically in this plot here, all of these points are things you get from different prompting strategies. Yes, they're technically above the line, but in the least interesting way possible. One way you can always get above the line is you take the point and you interpolate it with a random classifier. And this is like clearly making your model just worse. And these different prompting strategies behaved like interpolating with a random classifier. And then to see what contrastive losses do, we ran a bunch of Imagenet contrastive loss functions that people had proposed, and they are mostly on the blue line. This one is a bit of an outlier, and I think a great question is why. And I think this is getting a bit technical now. So here we are averaging over 5 distribution shifts. One of them is Imagenet A. Imagenet A behaves different from the other 4. I look into what is exactly going on here. Overall, even if this is an effect, it is much smaller than the effect you get from clip. Okay, cool. So what's left is the main factor is training distribution. I found this really interesting because like, the image text supervision part was the new thing in clip. And I think it's really, really great. I don't mean to like, diminish this in any way. I'm a big fan of image text supervision, but it's just good to know, does image text supervision inherently buy you robustness? Or is image text supervision just a tool to build more diverse pre-training data sets? And it's pretty clearly the latter. So I think the cool thing about clip is you can now take all of this data off the internet. You don't need to worry about sending it to Mtrack anymore. You don't have to worry about paying your workers to get labels like you would have before. And you get these nicely diverse pre-training data sets which then give you a robust model. Cool. So obvious next question is like, can we design even better pre-training data sets? So this is a paper that will hopefully be in archive a week from now. I don't really have time to tell you about it. At a high level, what we did there is just see how much different variation in terms of robustness is there between these different web data sources. And the answer is a lot. So now it's like getting very messy. And there are many lines in these scatter plots. Every line corresponds to one web data source. We did like Wikipedia, Reddit, Shutterstock, common crawl, and so on. Interestingly also, it's not that the high quality curated data sets like Wikipedia give you the best robustness in these, on these test sets. Like for instance, the Reddit one does really well on ObjectNet. And since the different pre-training data sets tend to do well on different distribution shifts, important questions like how can you combine them in a productive way? The simplest baseline idea is you just take the two pre-training data sets and you combine them and then train on a combined data source. The hope is that if you have both of them in there, the model is exposed to both types of robustness and you will get robustness to both. But that's not the case, unfortunately. Like in these scatter plots, if you look at the lines for two data sources and then interpolate them, then you really get the line in the middle. So you're diluting the robustness of the better pre-trained data set. Okay, so now we are at the end because we're also kind of out of time. So conclusions. At a high level, main takeaway is that the OpenAI CLIP model is a lot more robust than any of the image representations we had before. And the two big things that played into this is the ability to do zero-shot inference and then improve fine-tuning. And the other one is having a more diverse pre-training set. And I have no idea how to make diverse more concrete. I think this is a really great question. We talk about pre-training data sets being better. The only way that we really currently can establish this is by just training the model and seeing how well it does. And I think going forward, an important problem is going to be, can we design better pre-training data sets that give you robustness in a wide range of downstream tasks? Because it looks like machine learning is going the route, at least for computer vision, NLP, and so on, of using these large pre-trained models and then fine-tuning them for your task of interest. And then how should we design these pre-training data sets for the large models that we use in all of these applications? Cool. So this is all I had to say. If you want to play around with CLIP or any of these robustness data sets, you can go to these URLs, and I'm happy to take questions.
Was it the same number of parameters for the model?
Yeah, the number of parameters in the model doesn't really matter. So like in all of these scatter plots, you can make a model larger, smaller, you're only going to move along the line.
I see. Okay, great.
Thanks.
So since now you have, great talk by the way, and since now you have different data sets and you have like different, this kind of curves on each different data set, have you tried to measure the distance between two data sets and then try to track, say if there is a relationship between those robustness and those like distances?
Great question. If you tell me how to measure the distance, I'm happy to do it. So, I mean, there are obvious things like you can use a representation space of a pre-trained model. Then the tricky question is like, what pre-trained model do you use? Like, does it make sense to measure the distance between the CLIP pre-training set and another data set in the representation space of a CLIP pre-trained model? I'm not sure, but I think these are all really good questions. And like, if you have any suggestions for creative ways to measure distances, happy to chat, happy to point you to these data sets to get started. I think that's exactly what I would like to understand better.
Thanks.
Hi, so I have a question. And I guess looking at the CLIP data set comparing to Imagenet, found these gains. There's probably work with Imagenet compared to other computer vision data sets in the kind of robustness space. So is there any work there that might have hinted toward, these differences between the pre-training data sets?
It's a good question. Actually, there is not that much work that looks at variation in the pre-training data set. Sort of like at a high level, this Imagenet world, where we've seen a lot of progress over the past 10 years, was often happening in this paradigm. Here's a fixed training data set, Imagenet, and everything we do on the model side always starts with this training data set. So this idea of using different or larger pre-training data sets only really appeared in, let's say, 2018, in an increasing number of papers, when sort of like the model architecture gains started to slow down and people were thinking, oh, maybe we can use more data to make the models better. But we have pretty little systematic understanding here in terms of like different data sets. Because as I mentioned also, one big limitation was how do you build these pre-training data sets? So like having done this once, I can tell you classifying images into 1,000 classes for Imagenet, very painful. Like don't do this on many images. So this was, I think, one bottleneck, but with CLIP and this image text flexible pre-training, now the bottleneck is gone, and I think we can do a lot more interesting experiments.
looking at these plots, I'm just like, I'm super impressed that you have set so close to a linear fit, like obviously in whatever transformation you've done to your axes, but like, does it surprise you that the data fell so close to a line, or is this something you expected or can explain? No, this is very surprising. I agree with you. Like, by now I'm kind of used to it and I don't find it surprising anymore, but I also don't know when it happens. Like, we actually have a paper on this. It's called Accuracy on the Line. If you just Google Accuracy on the Line archive, you will find that paper where we more systematically go through this. And the thing is, it happens on many distribution shifts, but not all distribution shifts. And I think even just being rigorous about when this happens and when it doesn't happen is, I think, a very interesting question, because when it happens is a super nice guide for model development, understanding robustness and so on, and I think it's quite valuable, and I could tell you a lot more about this, how it already has been useful for model development. But yeah, at a high level, I think it's surprising. I don't know when it's happening. And then when you subsampled data to get points that were farther kind of on the left of this line, did you need to average over like multiple different choices of random subsample, or was it like pretty much whatever subsampling you used, you got the same value? Yeah, this one. This is exactly the question one of the reviewers asked for our NeurIP submission that I just showed. I hope I didn't de-anonymize the reviewer. No, I don't think I did. So this is a great question. For this experiment, and I think all the others, there's randomness from IID subsampling, right? It doesn't matter. Like, every time you do this, every sample, okay, the samples are fairly large, right? So maybe it shouldn't be that surprising, because if you have 1 million data points, okay, so yeah, the samples are large, but actually think about this more. You can push this to pretty extremes. Like, if you do this on CIFAR 10 and you sample subsets of size 500, they're still going to be on the same linear trend. And since we're talking about linear trends, another thing that's really cool about this, for Imagenet v2, and we also have these CIFAR 10 shifts, the red line here goes exactly through the origin. So like, the random classifier is also on the line. And on CIFAR 10, the linear trend goes to 10%, 10%, because it has 10 classes, so the random classifier is also on the line. Thank you.
So you mentioned the importance of the training data being more diverse in this CLIP data set. From what you know about the CLIP data set, from kind of like what you've heard and can share, like, in what ways is it diverse, do you think, compared to something like Imagenet, sort of concretely?
It's a good question, and since this is recorded, I don't want to get Chong-Wook and Oleg into trouble, okay. So I'm not going to tell you. Okay. They were very helpful with both the data set reproduction and guiding us at a high level what from their perspective would be interesting questions. So I can probably say that it's more than one source.
Let's take the other questions offline, and let's thank the speaker.